Previously, we have computed cohomology group of finite cyclic groups. Now, let's talk about cohomology of finite groups in general. Of course, finite groups are torsion, but it turns out that so are their cohomology groups, at least in positive degree. It turns out that if G is a finite group, then for every coefficient group A, every element of the cohomology groups of G with coefficient in A is gonna have order dividing the order of G. Let us give a quick preview of why this is true. The key idea here is that if G has a subgroup H of finite index n, then the multiplication by n map on cohomology groups of G is gonna factor through the cohomology group of H. This statement actually holds for any group G in general, not necessarily finite. However, if G is finite of order n, say, then the trivial subgroup is a finite index in G. In particular, it has index equal to the order of G. Thus, applying the previous proposition with this trivial subgroup in place of H, we get that the multiplication by n map should factor through the cohomology group of this trivial subgroup, which is 0 in positive degree. Thus, multiplication by n kills all the elements of these cohomology groups, and therefore all elements of this cohomology group must be torsion of order dividing n. We'll fill in the details of this proof in subsequent videos, but for now, let us introduce these maps that we have used here. These are called restriction and co-restriction maps. In general, if H is any subgroup of G and A is a G module, then we can always view A as an H module. And we can relate the cohomology of G with coefficient A with the cohomology of H with coefficient A via the following restriction and co-restriction map. So let us first define the restriction map, and then we'll define co-restriction map in the next video. The key idea behind both definitions is to use Shapiro's lemma. Recall that Shapiro's lemma gives us a way to relate the cohomology groups of G with the cohomology groups of H. More specifically, if B is an H module, then we can associate to it a G module, such that the cohomology groups of H with coefficient in B are going to be isomorphic to the cohomology groups of G with coefficient in this induced module. Now, what if B was already a G module? That is, what if we had started with a G module A and then apply this construction to A when we view A here as an H module? What is the relationship between A and this module? Well, we claim that there is a natural group homomorphism from A to this module, and thus applying the cohomology functors to it gives us a homomorphism from the cohomology group of G with coefficient A to the cohomology groups of G with coefficient in this module. Now, by Shapiro's lemma, we could identify these with cohomology groups of H with coefficient in A, and thus this composition gives us the restriction map. So that would be the definition of the restriction map. Now we just need to explain where this homomorphism comes from. Well, recall that by definition, this module is just a group of group homomorphism from this group ring to A that commute with the action of H. In other words, these are H module homomorphisms from the group ring to A. On the other hand, we could also identify elements of A with certain group homomorphism. Observe that since this group ring is a free module rank 1 over itself, all G linear homomorphism from it to A is uniquely determined by where it sends the element 1. This gives us an abelian group isomorphism between A and this group of G linear homomorphism from this group ring to A. Now, any homomorphism that commutes with G action must also commute with H action because H is just a subgroup of G. Thus, we have a natural way to view elements of A as elements of this group of homomorphism. Now, applying the cohomology functors on this map gave us this map, and then composing this with the isomorphism in Shapiro's lemma gives us the restriction map. Thus, for every subgroup H of a group G, we have defined a restriction map relating the cohomology group of G with the cohomology group of H. In the next video, we're gonna define a map in the other direction. These are gonna be called co-restriction maps.